In this lecture, we're going to talk about integration of indicator functions and also resulting convolution integrals. We will start by defining indicator functions. Suppose A is a set, then the indicator of A, or the indicator function of A, is the function 1a of t, such that it has two values. It's 1 when t is in A, and otherwise it's 0. These indicator functions are very useful to adjust limits of integration. Let's take an example. So suppose we wanted to integrate from 0 to infinity of t to the 1 half e to the minus t to the 3 over 2, multiplied by the indicator function from 0 up to 4, not including 4, of t. Well, that indicator function is basically 0 off of 0 to 4. And so what we're really doing is we're only looking at the area under t to the 1 half e to the minus t to the 3 over 2 between 0 and 4, because the area under the remainder of the function is the area under 0, which is 0. Technically, this would result in a improper integral because it's a semi-closed interval, so it's open at 4. But since t to the 1 half e to the minus t 3 over 2 is so nice, it's really the same as the Riemann integral. The limit in the improper integral will exist and it will be equal to the Riemann integral where we would have closed at 4. And so this then really is the integral from 0 to 4 of t to the 1 half e to the minus 3 over 2 dt. But we know that t to the 1 half e to the minus 3 over 2, that has a nice antiderivative, which is minus 2/3 e to the minus t to the 3 over 2. So we can evaluate this Riemann integral now using the antiderivative, minus 2/3 e to the minus t to the 3 over 2. We evaluate it positively at 4 and negatively at 0. The result is that we get 2/3 times 1. That's from evaluating it negatively at 0. The negative in front of the 2/3 cancels with the negative from the lower limit. So 2/3 times 1 minus e to the minus 8. When you plug 4 in and then you take a 4 to the 3 over 2, you get 8. So these indicator functions are particularly useful for convolution integrals. So let's define what a convolution integral is. Suppose f and g are functions that map the real line into the real line. Then the convolution integral is f star g of x. So that's the normal notation. And it's equal to the integral from minus infinity to infinity of f of x minus y g of y dy. So we first lag f and then we multiply it by g and then we integrate. And since the limit is from minus infinity to infinity, technically it's improper integral. However, assuming everything converges nice, we can think of this almost like a Riemann integral. And we could make the substitution z is equal to x minus y to obtain the integral from minus infinity to infinity of f of z g of x minus z dz. So this is also equal to f star of g. We might sometimes say a change of variables instead of substitution. Let's take an example. So suppose f is equal to x times the indicator 0 to root 2, and g is equal to x squared times the indicator 0 to the cube root of 3. Then we want to find this convolution, which you write as the integral from minus infinity to infinity of fx minus y gy dy. So to be able to solve this, we should first note that the square root of 2 is slightly less than the cube root of 3. So this is going to be important when we break it down in cases below to determine exactly what cases we have. So if we substitute in our values of f and g into this convolution integral, we find that we have the integral from minus infinity to infinity of x minus y times the indicator function from 0 to root 2 of x minus y times y squared times the indicator function from 0 to the cube root of 3 of y dy. So this isn't particularly nice because what we have is we have an indicator function that's evaluated at x minus y. We would really like an equivalent indicator function that's a function of just y. But that's easy to obtain because if we look at this indicator function, it's 1 when 0 is less than or equal to x minus y, and it's also less than or equal to root 2. And so we can just multiply through by minus 1 and we get that this condition is the same as minus root 2 being less than or equal to y minus x, and that being less than or equal to 0. and now we have y in the right direction. And then what we can do is we can add x to all three parts, and we get x minus root 2 is less than or equal to y, which is less than or equal to x, and this is equivalent condition. So we can rewrite that indicator function as the indicator from x minus the square root of 2 up to x, closed interval, of y. And so this simplifies the resulting integral down to the integral from minus infinity to infinity of x minus y times y squared times the indicator of x minus root 2 up to x intersect with the closed interval from 0 up to the cube root of 3 of y dy. So if you multiply those two indicator functions together, it's easy to see that they're the same as the indicator function on the intersection of these sets. However, this is still slightly complicated because this set now depends on x, and in fact it could be empty. Indeed, in the simplest cases, where x is less than or equal to 0, then the closed interval on the left side of the intersection is strictly below or to the left of the one on the right, or at most they intersect at 1.0. And so the area under x minus y, y squared times that indicator function would be the area under at most 1 point, which would be 0. Similarly, when x is greater than or equal to the cube root of 3 plus the square root of 2, then the interval on the left from x minus root 2 to x is strictly above the one on the right, and we again get 0. In the other cases, we would have when x is between 0 and root 2, then we have x minus the square root of 2 is less than 0, so we're going to start at 0, but then we're going to end at x. And the reason why we know we're going to end at x is because the square root of 2 is less than the cube root of 3, which we already determined above. In the next situation, when x is strictly between the square root of 2 and the cube root of 3, then x minus the square root of 2 is larger than 0. And so we're going to start at x minus the square root of 2. But since x is less than the cube root of 3, we're going to end at x. So those are the limits for the second case. And in the third case, when x is between the cube root of 3 and the cube root of 3 plus the square root of 2, we're going to still start at x minus the square root of 2 because we know that's larger than 0, just as above. But now, since x is at least as large as the cube root of 3, we will end at the cube root of 3. And so now the difficult part is actually done. All we have to do is we have to evaluate the three middle integrals using an antiderivative. However, what we can do is we can note by indefinite integration that an antiderivative of x minus y times y squared is x times y cubed over 3 minus y to the 4 over 4. You could add an arbitrary constant to get the indefinite integral, but as we know, we just need any antiderivative, so we can take that constant be 0. Also, when we're looking at this, we're thinking that x is a constant. X is a variable in the resulting function, but when we're doing this integral, we think of it as a constant, and then later we treat it as a variable after the integration. And so now to get these three middle integrals, all we have to do is use the right-hand side of this formula, and we would evaluate the first one positively at x. So in other words, we substitute y is equal to x into this formula, and we get x to the fourth over 3 minus x to the fourth over 4, which is going to give us x to the 4 over 12. And then we evaluate it negatively at 0, but substituting y is equal to 0 in will just give us 0. So we'll be left with x to the fourth over 12 in that case. In the next case, we'll value this integral using the antiderivative positively at x and then negatively at x minus the square root of 2. When we evaluate it positively at x, we get exactly the same value we got just above, i.e. x to the fourth over 12. When we evaluate it negatively at x minus the square root of 2, what we do is we just substitute y is equal to x minus the square root of 2, and we get x times x minus the square root of 2 cubed over 3 plus x minus the square root of 2 to the fourth over 4. In the final case, we evaluate it positively at 3 to the 1/3 and then negatively at x minus the square root of 2. The negative evaluation using the antiderivative is just exactly the same as the immediate step above. However, the first step, we have to use 3 to the third. So if we substitute y is equal to 3 to the third in above, in the first case we get x times 3 to the 1/3 cubed divided by 3. So that's just going to give us 3 over 3 times x. So that's just going to give us x. And then we also have to subtract off 3 to the third to the fourth and divide that by 4. Well, 3 to the third to the fourth gives us 3 times 3 to the 1/3, and then we divide that by 4, and we're left with 3/4 times 3 to the 1/3. And then the remainder part is exactly as the previous step, as we just mentioned. And the cases are exactly the same as just above. So in conclusion, we've defined an indicator function, defined a convolution integral, and what we've done is we've motivated how to use indicator functions to change the limits of integrals, and also how they're useful in convolution integrals. The actual use of convolution integrals will become clear in applications like system theory and probability. Thank you.